All right, ladies and gents, so we are here to talk about topic 5 today. We'll be talking a little bit about electrostatics. We'll be talking about electric currents. So here we got a brief history, ladies and gents, of electrical science. And you can see it's a very expansive history. The turn of the 1900s is when we saw things like Edison and Tesla, but it actually started in the 1670s with Robert Boyle. Now, some of the most important discussions were Benjamin Franklin when he talked about positive and negative charges in the 1740s, and also Michael Faraday, who talked about static electricity and current electricity. These are two of the largest and most important distinctions within the subject. Now, one thing that I think is very interesting is the huge gap that we see in some of these discoveries, right? Obviously, people in the 1600s were very interested in the idea of electricity, but it was a means of the tools and scientific perspective that allowed people to dive further. And it wasn't even until after Faraday and the discoveries that he made that you were able to have people like Tesla and Edison who had the electricity wars all around the world. So a quick review, ladies and gents. What is charge? For right now, charge is a very, very simple concept. It is the amount of electrons on an object, excess or deficient electrons. If you have excess, you are going to have a negatively charged object. If you have deficient, you are going to have a positively charged object. Now, charge is a fundamental property of things in nature, but that's something we'll discuss in particle physics. If you have equal amounts of positive and negative charges, that's when you have something electrically neutral. Now, putting all of this together, if we have two charges that are near each other, we're going to have electrostatic force. All right, so Coulomb's law is what describes electromagnetic force between two charges at rest. That's why this entire science is called electrostatics. Everything is static. You do know, and you should recognize, I hope, the idea of attractive and repulsive forces. You've been taught this since the 3rd grade. Now, this is really important because it relates directly to how we formulate this equation. You'll notice that we only place the absolute value of the charges in question into the equation. We do this because the direction of the force is dependent on the situation. Is it attractive or repulsive? But the magnitude is going to be the same if the charges and distances are all the same. Okay? So direction is dependent on the situation, the geometry, and the magnitude is dependent on the quantity or the variables. So a quick review, ladies and gents. We already talked about the idea of absolute values for charges. We do this because of the direction, okay, of attractive versus repulsive situations. We do know that the distance between them is going to be one of the most important, actually the most important variable because it is squared. But we do need to talk about something that's really important, the idea of K, or the proportionality constant. Now, K does have a value that's easy to remember, 8.99 times 10 to the 9, but commonly we always ask ourselves, well, what does K represent? So K represents a couple different things. 1 over 4 pi epsilon naught represents, first of all, a spherical geometry. Okay, so if we have a charge that is in free space, what it does is it creates a field around it in a 3-dimensional sense. Okay, so that's something we have to consider. That is what 1 over 4 pi represents. Epsilon naught, or the permeativity of free space, is all about how a vacuum permeates an electric field, or how any different substance permeates an electric field. Here you can actually see, ladies and gents, a small list of relative permeativities. So by definition, a vacuum is able to permeate an electric field very, very easily. So everything else has a more difficult time. You can see sulfuric acid at room temperature has a really hard time permeating an electric field. So what I want you to do, ladies and gents, is take a second, pause the video right now, and you can do the practice problem right here on the screen. Find the total force on the center charge. So here's just an example, ladies and gents, of when we have a particle like Q1 that is experiencing a force from more than one source charge, Q2 and Q3. What we do is we break this problem into two different pieces. Okay, the total force that Q1 is experiencing is the force from Q2 plus the force from Q3. Here's a quick practice question, ladies and gents. Pause your screens. When you unpause, the answer will be there. The question is, which answer best represents the total force on the object in the circle? So moving on to our next concept, ladies and gents, we have electric fields. So electric fields, by definition, are the force per unit charge that is experienced around a source charge. Now, the idea here is that if we were to place a test charge in the field around a source, that test charge would feel a point that is dependent on the value of the test charge only. Okay? So essentially what we're trying to do here, ladies and gents, is we're taking a source charge, Q1, and then we're placing an imaginary test charge. Here's our test charge here, and here's another one. All right, we're placing these test charges around our source so we could see what type of force a particle would receive depending on the amount of charge it has. So the key thing we really have to remember here, ladies and gents, is that this small positive test charge does not affect the other surrounding charges. It is an imaginary charge that we're placing into the situation, and this helps us measure the strength from the surrounding charges. Just like the Coulomb's law or the electrostatic force, the electric field is also a vector value. So that means if there's multiple charges, we can add those electrical fields together, like in the example below. So what does the electrical field look like? The electrical field, we know by definition, is force per charge. This force is the electrostatic force, as you can see the equation here. So as we plug in the values, how does it change? Well, what changes, ladies and gents, is the numerator. No longer is it Q1 times Q2, it is just Q1. By dividing by the value of the test charge, we have eliminated it from the equation. Here's a nice example, ladies and gents, of looking at the force on a test charge, Q naught, looking at the electric field at that same location. You can see they are essentially the exact same thing, only difference is we've removed the particle. And then we also have the exact same situation with a negative source charge, and all that does is flip the electrical field into the opposite direction. So we always need to ask ourselves, ladies and gents, what does electrical field look like? Well, there's two things we need to remember about this. Electrical field is first of all represented by the density of lines. The more lines there are in a space, the stronger the field is. So we can see here that example C is definitely the strongest charged object. It is emitting a lot of electrical field. The other thing we really need to remember is the direction. Okay? So we have to remember that positive particles point out, negative particles point in. Here we can see a couple examples of basic situations. These are three things that I highly recommend you are able to draw. The constant electric field, or the capacitor, is something we will discuss in detail. The point charge we will also talk about in detail. And the electric dipole is the simple idea of an attraction pair or a repulsion pair. But all three of these situations you should be able to draw. Go ahead and pause your screen, ladies and gents, and in a couple seconds you'll see the appropriate answer marked on your screen. Let's take a specific look at this point charge situation. Here we have a positive point charge that is emitting an electric field outwards. Particles B and particles A are at different locations within this electrical field, and as we can see, according to their vectors, are experiencing a different force. Now, if we are placing real particles into this situation, we have to consider a couple of different things. How did we get the particles there to begin with? In order for particle B to get this close to the charged particle, we would have had to have pushed it all the way from infinity, where the electrical field would be equal to 0. So what are we doing, ladies and gents? When we're pushing a positive charge towards a positive charge, we are actually doing work in this situation. And that leads us to start talking about things like potential difference. Here we can see the same point charge drawn with equipotential lines around it. The equipotential lines are drawn to show us that at the same distance, a charged particle will experience the same amount of force and have the same amount of potential energy. So in this reference right here, ladies and gents, we'll be talking about a positive particle that we are putting close to the larger one. So as we move this particle closer, we are experiencing a change in energy, right? As we get closer and closer to the charge, more energy is necessary to push it upwards. And what this does, ladies and gents, just like pushing a ball uphill, if we have to do work to push the object up, well, when you let it go, it has potential energy and it can move back downwards. And that's exactly what these equipotential lines are here to show us. As you travel from one spot to another, you are experiencing a change in potential energy or a potential difference. It's really important for us to be able to visualize what this idea of potential looks like for static charges. The bottom example here of positive and negative charges is the best way for us to think about it, because it also shows us the direction of that positive test charge. Okay, so perspective is really important. If we are dealing with a positive particle, as positives approach positives, it takes more and more work because we are working against the repelling force. If we have a positive test charge that is near a negative charge, well, here we have an attractive force. So that means no work is necessary by us. The work is being done by the attraction of the two particles. Geography is a great analogy when talking about the idea of potential difference in electric fields. If we want to hike from the 1500 elevation to the 2000 elevation, there are lots of different paths we can take. We can take the very long path here. We can take the short path. We can even create a zigzag or snaking path that gets us up to the top. But either way, ladies and gents, no matter what, you have gone from 1,500 feet or meters in elevation to 2,000 in elevation. The amount of work that it takes to go from 1,500 to 2,000 is always going to be the same. Work is done as you go up the hill. If you were to walk along one of these lines, you would actually be doing no work. You're not changing your elevation. You are simply moving along the same potential. We're going to revisit this topic of electrical potential when we talk about field theory. Now what I want to jump to, ladies and gents, is circuitry, because a couple definitions change when we start talking about circuitry, especially potential difference or voltage. But we got to start talking about what a circuit is and what certain rules apply. So to make it simple, ladies and gents, a circuit consists of a power source and a resistor or object that utilizes the energy provided. A circuit is only complete when both ends of the cell are connected to the resistor. Now, potential difference or voltage still has the same definition in terms of units, within circuits as it does in electrostatics. Voltage or potential difference is still the amount of energy per charge. But here, the end and beginning of the journey is very well known. It is the beginning of the battery and the end. So voltage is the amount of energy needed to move a charge all the way through the circuit. Once we have a cell or energy source that is providing power to the electrons, they're going to flow through the electrical wire. This rate of flow is what we call current. Current is always noted as the capital letter I and is measured in amps or amperes, which is a fundamental unit in the SI system. Now, current flows in just one direction. It's called direct current. This year, we'll also be talking about alternating current. Now, current is really interesting because it also has what we call drift velocity. Looking here, we can see that the rate of flow of electrical charge does depend on the physical velocity that these electrons travel in the wire. Now, a quick word about objects traveling through the wire or electrons traveling through the wire. We have to make sure we understand the concept of the sea of electrons. So solid metal wires here, like the one I'm drawing, what they do, ladies and gents, is they tend to push all of their electrons out, or their excess electrons, I should say, out to the exterior, that surface area of the wire. So electrons, ladies and gents, are actually flowing here on the surface of the wire. And this is what we call the sea of electrons. So as these electrons are moving, we can actually look at their physical velocity from the current. The last thing we need to talk about, ladies and gents, is resistance. Now, resistance is the final factor in the proportion that we call Ohm's law. Resistance, by definition, is the proportion or the ratio of potential over current. And as you can see, this creates a perfect little equation for us, which we call Ohm's law. Ohm being the unit of resistance. It's also important to note that we can define resistance in terms of a property called resistivity. So resistance is directly proportional to resistivity times the length of the wire divided by the cross-sectional area. So remember, when we're looking at this, ladies and gents, our rho here, our fancy looking P, this is resistivity. Resistance is for an object. Resistivity is a property of the material. This right here is a funny little image that allows us to sort of visualize what these three quantities mean and what they actually do to electrons. So as you can see, the volts, or the potential difference, is what pushes the electrons through the wire. The ohms are trying to restrict the flow of the electrons, right? They're trying to crimp the wire down so they move more slowly. And the amp is the rate at which they flow through that hole. A quick review about how we measure these quantities. Voltmeters are always put in parallel. When they have infinite resistance, that really allows for us to use them properly. So when we add 1 over the resistor or 1 over infinity, we're essentially adding 0 to the circuit. There is no extra resistance being added. Ammeters, on the other hand, are the exact opposite. They are put in series with their objects, and the reason for that is because they have 0 resistance. This little chart right here, ladies and gents, is the end-all be-all of series versus parallel circuits. This is what you need to remember. It has all the essential information: what they look like, what happens to the current and voltage in these two situations, and how you can find the equivalent or total resistance. And remember, this is essential because this is how you begin solving any of the problems that we have with circuits. We always want to find equivalent resistance first so we can find the total current coming out of the cell or battery. So what does the last chart mean for us in reality? Well, this picture shows it all. When we wire things in parallel and each branch receives the same amount of voltage, all of the lights are able to be equally as bright. They're all receiving and utilizing the same amount of power, considering they're the same resistance. Now, what's also interesting about parallel is that we could take one of these light bulbs and it could go out and the other two would still keep functioning. So there's a lot of advantages with parallel circuits. Now in series, we can see a couple different things. You can actually see first that this bulb up here is definitely brightest. It has a much larger lit area than the one in the very front. So all three of these things have a different amount of power that they're using. And if they're connected one after another, if I were to just take one out of the situation, all three would turn off. Because if electricity has nowhere to go, if it's not connected to the end part of the battery, it will not flow. Here's a nice example, ladies and gents, of how we simplify a circuit. And just look right here to the right, you'll see the number one rule that we always follow. Start from the outside and work your way in towards the cell. This is a nice little image, ladies and gents, that shows us Ohm's law, the original form, V is equal to IR, and how we can translate this to calculate every other variable within the equation. It also shows us the graphical representation, and it's really important, ladies and gents, to realize that a higher slope means a higher resistance. Now, the other thing I want to point out, ladies and gents, is what is on the axes here. Here you have voltage versus current. You can see here on this slide we actually have the opposite. Here we have voltage on our X and current on our Y. Please be very careful when you're reading these graphs and always pay attention to what's being graphed. So this is really important because as we look at this, we're actually seeing not just ohmic devices, not just objects that follow Ohm's law, but objects that do not follow Ohm's law. So we actually have two things here. We have filament light bulbs and we have LEDs that have very specific functions. So as the LED becomes active, what happens is its resistance approaches zero. A filament, on the other hand, is the exact opposite. As it gets hotter and hotter, its resistance goes up. As we combine and create more complicated circuits, we have to keep in mind Kirchhoff's laws. Kirchhoff's laws are really about the conservation of charge and the conservation of energy. So law number one is essentially saying that anything that comes into a junction, any current that comes into a junction, must also leave the junction. The second law tells us more about the power or the energy source that comes from the cell. And the second law says that the energy provided by the cell must be used within the circuit. When we start talking about the power delivered by the cell, we can also begin to talk about EMF, right? EMF is the total amount of work per unit charge. So it is the amount of voltage given to that electron to push it all the way around the circuit. So building on this idea of Kirchhoff's laws, we also have to remember that the energy provided by the cell and the energy used by the resistors can also be discussed in terms of power. And there are a variety of equations for us to use. So now I want to jump in and start talking about the cells or the batteries, the power sources of circuits. So the very first cells or battery was created in France by a scientist named Leclanche, but since then we've had lots of development. Now, a primary battery is still reminiscent of the very first battery we made. They are batteries that after they are used, they are discarded. They cannot be recharged. A secondary cell, on the other hand, is one that can be recharged after they've been discharged. So this new development has allowed us to begin recycling our material. So how can we relate this idea of EMF to a battery? Well, if we look at a battery and the current that it provides, This slope right here represents something very specific, but EMF, ladies and gents, is actually going to be the y-intercept. It is the initial amount of voltage that's being given by the battery. And if we take the slope of this, rise over run, we end up with voltage over amps, which is equal to resistance. This is not just any resistance though, ladies and gents. This is the internal resistance of the battery. So when we begin to look at circuits, we actually have to say that the EMF, the energy provided by the cell, is equal to the voltage used by the internal resistor plus the voltage used by the external resistor. Here we can also see that a battery's voltage or potential difference varies not only with time, but the amount of resistance that you have in the circuit. So what we're showing here, ladies and gents, is that the larger the resistance, the longer our battery is going to last. So our 62 ohm resistor allowed the battery to give us 140 hours of service time, as where a 4 ohm resistor gave us maybe 8 to 10 hours of service time. So these resistors, by restricting the flow of electrons, allowing them to move slower, gives us more operating time. Finally, ladies and gents, let's start talking about magnets. So magnets, very similar to positive and negative charges, we have north and south sides of a magnet. Now, also similar to electrical field, one of them pushes out, one of them pulls in. And as you can see here in all of these drawings, north is pushing out, south is pulling in. So when we're drawing these, ladies and gents, whether they're repelling or attracting, we have that same sort of relationship, but it's north and south, not positive and negative. So Earth's magnetic field was one of the very first ones that we began to interact with, and we've been studying it for a very long time. There's some really interesting things. First of all, the magnetic field absolutely saves us time and time again from cosmic radiation or solar coronas that are spitting plasma out into the solar system. As we have analyzed and looked at the magnetic field, we've actually also seen that the magnetic poles of our planet move around. So it's a very, very interesting topic in geophysics and how this is being created and what's causing it to move around. One of the coolest pieces of evidence we have of a magnetic field is auroras. And this is actually one of the ways that we can tell that other planets have magnetic fields, because we can see auras or auroras on their poles as well. So you can see here in this image that Saturn has an aurora around its southern pole. So this is telling astronomers that there is an active magnetic field here. Cosmic radiation is being sucked in by the magnetic field. It's interacting with the atmosphere, causing this glow. That's what causes this phenomenon. So it's easy for us to say, it is a logical jump for us to say that, hey, if we have a core of the planet that is creating our magnetic field, it's possible that there's something similar happening on this planet. But Saturn is a gas giant. How does a gas giant that's not supposed to have a planetary core create a magnetic field? So we start diving into some really, really cool questions. We have a few different units that we utilize to measure the magnetic field, but when we're talking about B, the magnetic field quantity, we always use what is called the Tesla. Now, the Tesla is a derived unit. It is the flux per unit area, and by flux, what we really mean is the number of field lines that go through a specific unit of area. Electrical currents also create a lot of interesting phenomenons that happen. So electrical currents actually create a circular magnetic field around them. So this looks similar to the equipotentials that we were drawing earlier, and it does have a similar effect in that the farther you are away, the less magnetic force you will receive. Now, this is a really interesting law here, ladies and gents, and is commonly shown by giving a thumbs up, where your thumb is representing the direction of the current And your fingers, as they curl around, create the direction of the magnetic field around the wire. Here you can see a nice diagram of exactly what I'm talking about. As the current is moving up through the wire, we place our thumb up to mimic that motion, and you can see that the fingers on the thumbs up are moving in a clockwise direction. So that tells us that we always use our right hand, that when the current is moving up, that magnetic field will be moving around the wire in a counterclockwise direction. An interesting thing we've been able to do with this idea is taking a loop of wire, and if this loop of wire has magnetic field all around it, we can actually create a stronger magnetic field, and we can amplify these effects. And if you start piling these coils on top of each other, you can create an even more powerful magnet. And so as you can see here, ladies and gents, just using current, I can essentially create a magnet here where one side is going to be north, the magnetic field is leaving, and one side is going to be south, magnetic field is entering. This solenoid is essentially a magnet. And we can actually calculate the amount of magnetic field in a solenoid using this equation right here. Mu naught represents the permeability of magnetic fields, N is the number of turns, and I is the current. So one thing I want to point out here, ladies and gents, and I think it's really important, when we are looking at the solenoid, and if we want to say this is essentially creating a new magnet, I want you to remember this. The south side of the magnet is where the current enters the solenoid. The north side of the magnet is where the current leaves the solenoid. So what happens when a particle enters a magnetic field? It will now experience what we like to call the Lorentz force. The Lorentz force has a very, very simple equation. Force is equal to QVB times sine theta. Now Q, V, and B are very, very simple. The charge of the particle in question, its velocity, and the intensity or strength of the magnetic field. It's sine theta where things get a little bit more interesting. Sine theta is the angle between the velocity vector and the vector of the magnetic field. Now what this shows us here, ladies and gents, by using sine, essentially what we're saying is that 90 degrees is equal to maximum force. Okay? If these two things are perpendicular to each other, that particle will receive maximum force. If these things are parallel to each other, right? Velocity and B field are parallel to each other. What we have here is zero force. Here's a little image to show you a visual difference of what happens. So you can see as the positively charged particle enters the electrical field, it simply moves with the electrical field. A positive particle will be repelled by positives, it will be attracted by negatives, so the particle will make its way towards the negative plate. Now when a charged particle enters a magnetic field, it is very, very different. It does not move with the field, it moves perpendicular to the field. So you can see here this charged particle is no longer going towards one of the magnets, it is moving up, out of the field in a new dimension. So these are our first three-dimensional problems in the IB. We can visualize this Lorentz law using what we call the right-hand rule. So the right-hand rule only applies for positive particles, and you can see here that each part of your hand represents something different. So the direction your thumb is pointing is the velocity of the particle, your fingers represent the direction of magnetic field, and your palm is showing us the direction that the force will experience. Now, how do we do this for our negative particles? It's really, really simple change, ladies and gents. For our negative particles, all you have to do is use your left hand, and you keep the exact same format. Thumb is velocity, fingers are field, and palm represents the direction of the force. So how do we deal with this, ladies and gents? There's a number of different ways. Now, what happens with a wire? what happens when we put a current through a magnetic field? Now, it's slightly different, ladies and gents, but it's a really, really simple change. If you know how to use your left hand with the negative particles, and you understand that thumb is velocity, fingers are field, and palm is force, what I want you to do, ladies and gents, is I want you to switch the values of your palm and your thumb. So now your thumb represents the force the wire will experience. The pointer finger or your fingers represent the direction of field, and your palm is showing the direction that the current flows. Now the equation is very, very similar. It is still sine theta based, but instead of QVB, we use BIL, magnetic field times current, times the length of wire exposed to the magnetic field. Very last thing for us to talk about, ladies and gents, is Lenz's law. So this is going to be essential for our next topic in understanding electromagnetic circuits, or how we generate alternating current. So Lenz's law, ladies and gents, says that if we use a magnet to induce a current, if I push a magnet towards a loop of wire, it will create a current by moving those electrons. But Lenz's law says something very, very special here, ladies and gents. It says that the current created will oppose the change that produced it. So as we can see here in example number 2, our center column, as the magnet is pushed down, ladies and gents, a current is created so that the magnetic field from our curl rule is going upwards, right? So it is fighting the magnetic field that's creating it. And the same thing happens if we take the magnet away and we cause the electrons to move in the opposite direction. What that's going to do is it's going to cause the loop of magnetic field to fight the change. I know this is complicated, ladies and gents, but we're going to be diving into Lenz's law a lot more in the next couple weeks, so just stay tuned.